Okay, so the title of this video should be Am I Insane? Intel Manual. I'm starting to make these videos for the reasons right here. I'll let you pause and read those. I'm big on saving time, so let me go ahead and just get to it. This is the first video where I'm going to go ahead and start reading the Intel Manual because I love assembly language and I love understanding the architecture of the CPUs I'm working with. And apparently the AMD and Intel architecture design is the same. So for this first video, the real objective is just for us to get an idea of what is inside the Intel manual. So when I click that link, I go to this website, Intel 64 and IA32 Architecture Software Developer Manual. And it was published in 2016, but updated as recently as February 4th, 2019. And I wonder what the IA stands for. Maybe Intel Architecture and then 32 as in 32-bit. If you need help understanding what those numbers 64 and 32-bit instruction set, what those numbers mean, I have a video on that. But getting into the world of reverse engineering and just studying assembly language, people say to look at the Intel manual so often that I thought I would do that. And I thought I'd bring you along with me. So we're going to skip this first one, keep going, 4-volume. For the sake of this video, I will not even get through that much, so let's just go to this 2-volume set and get started. And I want to get down to the meat of things pretty quickly here, but just to briefly go over the contents, it looks like the whole first chapter is about the manual itself. The second chapter is all about architecture, and then they break each one of their chips down. I think what I found was it's really redundant, so that's why when creating this video, came up with the idea that I'd start with Chapter 3, the basic execution environment. And that happens to start on page 63, so let's jump there. And then I split the screen so we'd have a chance to reflect together, and I'll provide you questions to help keep your focus throughout this reading. Again, yeah, maybe a little insane to do this, but the reasons are clear enough right here. Rather than research alone, let's research together. So this chapter describes the basic execution environment of an Intel 6432 processor as seen by assembly language programmers. It describes how the processor executes instructions and how it stores and manipulates data. The execution environment described here includes memory, which can be referred to as the address space. It includes general purpose data registers, segment registers, the flag register, and the instruction pointer register. If these concepts are confusing or new to you, I really suggest watching Ben Eater videos on his 8-bit computer. When you watch somebody wire an 8-bit computer together and create their own registers and create everything that's needed for a computer to work, you'll be more comfortable with terms like those. So here we go, 3.1, Modes of Operation. The 32 architecture supports 3 basic operating modes: Protected Mode, Real Address Mode, and System Management Mode. The operating mode determines which instructions and architecture features are accessible. So that's a little confusing. The first sentence says the architecture supports 3 basic operating modes. So you're telling me that each of these modes are an operating mode? So all 3 of these, protected, real address, system management, they're operating modes. And then the next sentence said the operating mode determines which. Are you saying all 3 modes determine which instructions and architecture features are accessible? Like, this is a big security sounding thing to me, so rather than type a binary question like I just asked there, let's come up with a better question like, what are the 3 operating modes of a 32 chip, question mark. And then I'll just tag on to here, are they all responsible for determining access? Protected mode. This mode is the native state of the processor. Among the capabilities of protected mode is the ability to directly execute real address mode. 8086 software is in a protected multitasking environment. Among the capabilities of protected mode is the ability to directly execute real address mode. 8086 software in a protected multitasking environment. That sentence does not jive very smoothly, but I guess the takeaway is that from protected you can go to real address mode. This feature is called virtual 8086 mode, although it is not actually a processor mode. Virtual 8086 mode is actually a protected mode attribute that can be enabled by or enabled for any task. Real address mode. This mode implements a programming environment of the Intel processor. with extensions such as the ability to switch to a protected or system management mode. The processor is placed in real address mode following power up or a reset. Alright, so a lot to unpack there. I can ask a question like, what is the default mode when powering up, question mark? And this question might be fun to say something like, which mode is the most flexible? But let's learn what this SMM is. This mode provides an operating system or executive with a transparent mechanism for implementing platform-specific functions such as power management and system security. The processor enters SMM when the external SMM interrupt pin, so I wonder if we could see that somewhere, SMI number. Well, when this is activated, or an SMI is received from the Advanced Programmable Interrupt Controller. That is definitely a word I've seen before, definitely worthy of a question. What is APIC? So the simple answer you can get right now is that it's the Advanced Programmable Interrupt Controller, but I'd have to do some research later on to figure out what that could mean. In SMM, the processor switches to a separate address space while saving the basic context of the currently running program or task. SMM-specific code may then be executed transparently. Upon returning from SMM, the processor is placed back into its state of prior system management interrupt. SMM was introduced with the Intel 386 SL and Intel 486 SL processors and became a standard 32 feature with the Pentium processor family. So, Intel 64 architecture adds IA32E mode. This mode has two sub-modes. Okay, so at least everything we just learned applies to 64-bit. The first sub-node is Compatibility mode. Compatibility mode permits most legacy 16-bit and 32-bit applications to run without recompilation under a 64-bit operating system, so that's nice. What allows a 64 chip the ability to run old 32-bit code? So thank you, compatibility mode. For brevity, the compatibility mode is referred to as compatibility mode. The execution environment of compatibility mode is the same as described in section 3.2. Alright, that's coming up soon. Compatibility mode also supports all of the privilege levels that are supported in 64-bit and protected modes. Legacy applications that run in the virtual 8086 mode or use hardware task management will not work in this mode. So that might be something I should note here with the little star. Legacy code using virtual 8086 still won't work. Compatibility mode is enabled by the operating system on a code segment basis. This means that a single 64-bit OS can support 64-bit applications running a 64-bit mode and support legacy 32-bit applications. Alright, that is completely redundant. Here's something new. Compatibility mode is similar to the protected mode we had just read about. Applications access only the first 4 gigabytes of linear address space. Compatibility mode uses 16-bit and 32-bit addresses and operand sizes. Like protected mode, this mode allows applications to access physical memory greater than 4 gigabytes using PAE, Physical Address Extension. So the question is, what is physical address extensions used for? And apparently a good answer would be, it is used for applications to access physical memory greater than 4 gigabytes. The second sub-mode is 64-bit mode. This mode enables a 64-bit operating system to run applications written to access 64-bit linear address space. Down here it says 64-bit mode extends the number of general-purpose registers and SIMD extension registers from 8 to 16. General-purpose registers are widened to 64 bits. The mode also introduces a new opcode prefix XREX to access the register extensions. 64-bit is enabled by the operating system on a code segment basis. Its default address size is 64 bits. Its default operand size is 32 bits. The default operand size can be overwritten on an instruction-by-instruction basis using REX opcode prefix in conjunction with the operand size override prefix. So I'm not sure why it's saying REX unless that's what you're typing in your assembly code, but I had always known that the registers down here that start with R and then a number, those were the registers for those 64-bit systems. Okay, let's just summarize the 64-bit mode term. What two submodes exist for 64-bit? Okay, so we got compatibility and then 64-bit mode. That's a funny name. If I was in charge of naming it, I would name it like promotion mode because that's what it does. So let me throw that question here. What does 64-bit mode actually do? And it sounds like it just promotes the computer's ability to use 32-bit instructions. It promotes it to a 64-bit space, even if the operand is only 32 bits. Okay, so this goes on to explain quite a bit more about the modes, and that's when we'll quit the video. So this first video could just be like the Intel chip modes video. And this term opcode prefix is really nagging at me, REX, so let's go do some additional research, then come back, finish the 2 paragraphs, then we'll finish the video. We made it almost to all the way done with page 64. Anyways, I remembered this cool website here. Apparently it's not secure, but it's useful. And what I was able to do is run a simple C program. It's like a prime number generator. And anyways, I remembered that I had the ability to compile it using x86 32-bit or x86 64-bit. And so I thought to myself, why don't I just look at those register names? After a website like this, ellcc.org, gives me that assembly. And lo and behold, here it is. So right after the main function begins, you're going to start seeing that difference. The first thing and again, this is the exact same program. So in the 32-bit program, we're going to push to EBX, but over here we're going to push to RBP. All of these are R's, and over here these are E's. And going down here, you'll still see the use of E's registers, EDX, ESI, ECX, etc. So here I found that REX prefixes are instruction prefix bytes used in 64-bit mode, and they do the following. They specify GPRs and SSE registers. They specify a 64-bit operand size. And then this prefix will go ahead and specify extended control registers. It says here, not all instructions require REX prefix in a 64-bit mode, and a prefix is necessary only if an instruction references one of the extended registers or uses a 64-bit operand. Oh, so in the case of 7 plus 7, that's ridiculous, and it wouldn't do it, I assume. If a REX prefix is used when it has no meaning, it is ignored. Only one REX prefix is allowed per instruction. If used, the REX prefix byte must immediately precede the opcode byte or the escape opcode byte. Cool, so escape is 0FH. When a REX prefix is used in conjunction with an instruction containing a mandatory prefix, the mandatory prefix must come before the REX. So the REX prefix can be immediately preceding the opcode or the escape byte. For example, all this nonsense with a REX prefix should have REX placed between F3 and OFE6. Other placements are ignored, and the instruction size limit of 15 bytes still applies to instructions with the REX prefix. So that next paragraph here said that this 64-bit mode is enabled by the operating system on a code segment basis. Cool, so that jives with what we had just read, that only if it's needed. Its default address size is 64 bits, and its default operand size is 32 bits. The default operand size can be overridden on an instruction-by-instruction basis using a REX opcode prefix in conjunction with an operand size override prefix. Jumping back to this other page, I eventually found the word override in the description. Apparently this W here is for width, so setting REX width can be used to determine the operand size, but does not solely determine operand width. Like the 66H size prefix, 64-bit operand size override has no effect on byte-specific operations. Later it says if the 66H override is used with REX and REXW equals 0, the operand size is 16 bits. So REX prefix allows a 64-bit operand to be specified when operating in a 64-bit mode. By using this mechanism, many existing instructions have been promoted to allow the use of 64-bit registers and 64-bit addresses. So that'll be good for today. We got to page 64 right at the 3.2 overview of the execution environment, so the next video will pick up right there. But in summary, we learned that there are 3 operating modes in a 32-bit chip, and when we move to 64 bits, there's just these 2 additional sub-modes, and it looks like they both are thinking, or at least designed, to allow 32-bit stuff to work. So nothing really major there. We got a couple keywords like this advanced programmable interrupt controller. I'm sure I've seen that before at security conferences. So there's a vocab word. Here's another one, the physical address extensions, or PAE. I'm positive that'll show up again in this manual. But that'll be it today. I hope you gained something from me doing this, and I look forward to your comments, suggestions, and questions. If nothing else, just me talking to a computer throughout this process is actually extremely helpful. So if you found yourself at this video, you might want to do something similar as well when you're learning something really complex and difficult, like reading the Intel manual.